going to come next. But before we jump into it, let me point out a few things. First, I put a link to this TED Talk by Bill Gross, which I highly recommend watching. It's actually quite interesting, and it's related to this idea of non-imaging optics. We will continue this lecture on Thursday. So this week, our hope is to lay the foundations of non-imaging optics. Next week, we'll deal with radiometry, photometry, which are somewhat different concepts, but very important for measurement and quantifying non-imaging optics. And of course, next Thursday, we have the team presentation. So keep this schedule in mind. Are there any questions before I get started? Okay, I guess not. So everyone's in good shape. Oh, also keep in mind that on the website, I have said that the assignment 2 is due September 22nd. So keep that in mind. That is the end of this week. Okay. Okay, we'll talk briefly about that later. Okay, let's begin. Let me just make sure we are recording. Okay, good. Okay, so we're going to talk about non-imaging optics, but before we understand what non-imaging optics is, we need to have a good understanding of what imaging optics itself is, right? So let's review what imaging optics is and what we have seen so far. So imaging optics, as what the name implies, is used to form images. So what does that mean? So if you think about an optical system as a black box, an imaging optical system essentially forms the image of an object. So if you're an object or a scene, an image is formed. Now, what does that really mean? That means that if you have a point P on an object and you have rays of light emanating from that point, you have a corresponding point P prime on the image onto which all these rays, which come from P, essentially converge. Okay, and I assume you also saw what virtual images were. So in the case of virtual images, the rays will appear to diverge from that point, but we'll talk about real images for now. So in that case, it converges, the rays actually converge to the point. So what's important is the fact that light, essentially there is a unique one-to-one mapping from the point P to a point P prime. Okay. Light from point P is captured by the optics and imaged onto P prime. There is a unique one-to-one mapping between the points in P and P prime. That's the key concept in imaging optics. Let me repeat what this means. What this means is that if you take any point of the object, you should be able to find a corresponding point on the image. So it's a one-to-one mapping. 1 point here maps to 1 point here. Now, in the case of non-imaging optics, which is conceptually drawn here, what we're trying to do is we're just trying to take the energy from some source like the sun and send it to the receiver. Okay, so the key difference is that we haven't formed any image. So we're simply taking all the energy we can from here and send it here, which in other words, which means that there is no one-to-one mapping. Okay, so a point here can map to any point here or many points here. That's the key difference. So there's a very fundamental kind of a difference, and I need you to understand this conceptually. So imaging optics, there's this one-to-one mapping. In non-imaging optics, in general, there is no one-to-one mapping. It's a one-to-many mapping. Okay. So in non-imaging optics, just to summarize, the goal is to create a desired irradiance on the receiver for a given light source. There is no one-to-one mapping of the points on the source to those on the receiver. And this will become clearer as we go along. Let's consider a more detailed situation of a light from an object EF. Okay, so this is an extended object, point E, point F. Okay, and this is the optical axis, this central line here. Now, CD is our optical element. Okay, it doesn't need to be a lens. Let's just call it an optic. Then an image is formed at AB. Okay, so point A and point B. Now, if we think about imaging optics, what happens is that every point, let's pick a point F on the object. All the rays that come from F essentially pass through the optical element CD, and that gets converged. So this ray, for instance, comes here, hits this is an edge ray for F, hits the edge of the lens or optical element here at C, and it bends towards A. The other ray, which is another edge ray for F, hits the other end of the optical element and bends towards A. So all the rays, the concept here is that all the rays that are coming from F and also are captured by D end up converged to the point A. Okay, and you can pick any point on the object, let's say point P, the same thing happens. All the rays from here, okay, after it passes through the lens, gets converged to a corresponding image point Q. So F is now mapped to A, P is now mapped to Q, E is now mapped to B, if this is a regular lens. A conventional lens, of course, the image is flipped, right? Laterally inverted, as you saw in your class on geometrical optics. So that's why F goes to A, E goes to B, and the object is essentially flipped upside down. Okay? So this, if you think of this as a conventional lens, light is actually concentrated, right, in a sense. The light from point F is concentrated onto the point A. And that from E is concentrated to B, and from P is concentrated to Q. And we can, of course, define a magnification factor as the ratio of the size of the image divided by the size of the object, or DI, which is just the location of the point Q, divided by DO, which is the location of the point P. Okay, all of this you have seen before, and this comes from geometrical optics or imaging optics. Okay. Now, how will we think about this from a design point of view? So, in other words, how would you design an imaging system with lenses? Which again is a review because you saw this before. So let's consider the simplest possible imaging problem, which is imaging one point. Okay. In other words, we have a point object to a point source at P, and you want to form its image at Q. Now, we know from geometrical optics that the way to do this is to ensure that any ray that comes from P, when it reaches an interface between, let's say, air of refractive index 1 and, let's say, some material like glass with refractive index n, it says that any ray, when it reaches that interface, undergoes a refraction such that it bends towards Q. Okay, that's this example here. Now, this is a very important example, which is referred to as a chief ray. This ray essentially passes straight through with no bending. And the only reason for that is because it is normal to the surface where it is incident. Okay, it goes straight through. And all the other rays undergoes refraction in the same manner. Now, you can define this surface simply by defining how much each of these rays have to bend, right? You can draw another ray here, how much it bends, another ray here, another, and how much the angle at which these rays bend defines the surface here. And this is referred to as a Cartesian surface or a Cartesian oval. Okay, it is essentially the surface such that each point on it has only one ray of light from P. Okay, so each point here, like R, has a ray of light from P, which is this straight line right here. Okay, then the surface can be chosen to focus all rays of light from P to Q. So what that means is that this ray of light at point R has to bend such that it goes to Q. And then from here, by knowing this bending angle, you can select what the orientation of the surface should be in order to satisfy the Snell's law of refraction, which you saw before. Okay, so that way you can actually define the surface. A simpler way to think about this is defined by what's called the Fresnel's condition of Fresnel's law, which basically states that the optical path must be the same for all rays from between the corresponding points. Okay, and what that means mathematically is very simple. It means that if you follow the path of light through one ray, let's say P to R, it has traveled in air through a distance d, and then it travels from R to Q with a distance, let's say d1, but in a material like glass. Okay, so that's one path of the ray, one ray. Another path, so that's if the optical path is then defined as d times 1, the refractive index of air, plus d1 times n, the refractive index of whatever material this glass is. Okay, that's the left-hand side. What Fresnel's principle says is the optical path must be the same for all rays, which means that whether it's this ray or this ray, the total optical path must be the same. So if we follow this ray, the optical path is simply this capital D plus capital D1 times n. So D plus n times D1 equals capital D plus n times capital D1. Okay, this is another way to define the surface. So this condition actually arises from Fresnel's law as well. The Snell's law as well. So you can actually prove this from Snell's law for small angles. So based on that condition, you can actually define the surface. So by knowing the simple geometry and the locus of these points, then defines this Cartesian surface. Okay, so in other words, if you were asked to design an optical system that images one point to another point, you should be able to simply draw the rays and define that surface based on your knowledge of refraction or your knowledge of just saying that the optical path lengths must be the same. Now let's try to extend this to more points. Okay, let's say we want to image 2 points. Okay. First, before I move on, there's another point to keep in mind here. Here, when we are imaging a single point, you can see I can actually define a surface here such that all the rays, I can draw any ray I want here, can be focused to a single point Q. Okay, this is very, very important. What that means is that I can actually form a perfect image of a point source with a single surface. Okay, it's a little bit abstract, but you can imagine, right? You can imagine drawing a ray in any angle you want, right? Because every ray is a little bit different. I can change the shape of this surface such that any ray that comes in here bends towards Q. So let me repeat this one more time. If I have a point source, a perfect point source, I can actually design a lens to form its perfect image with no aberrations. Okay, this is in general not possible, as you will see, and you probably saw in your lectures on geometrical optics, but if you have a single point, it is possible. Now, if you have 2 points, the conclusion is that we need at least 2 surfaces. So if you have 1 point, you can do that perfect imaging with 1 surface. The 2 points, the conclusion, as you will see next, is that we need 2 surfaces, as shown here. So we have 2 points here, E and F of the object, and you have 2 surfaces, 1 surface here, another surface here, and everything outside is air. The inside here, let's say, is glass. So rays bend here again, reach A, bend here again, reach A. You can actually show that by changing by selecting the shape of surface 1 and surface 2, you can actually take any ray that comes from 2 points, E, F or E and make them converge to two other points, A or B. We need two surfaces to do perfect imaging for 2 points. Okay, this is again a very, very important but simple conceptual idea. Two surfaces can be designed such that 2 points are imaged. Of course, each surface here will bend the light a little bit, and this will bend the remaining amount, right? And it goes for all the rays. So you have to do an optimization problem here for all the rays here and all the rays here such that they end up at these points as desired. Okay, and you can actually analytically solve these. We won't go into the mathematics, but it's more important for you to appreciate this conceptually. So in this particular case, again, all the rays from F end up at A, which is here, F, end up at A. You can draw any ray you want, and I can pick these two surfaces such that they always end up at A. And all the rays from E, again, you can draw any ray you want. I can draw this surface and this surface such that they all end up at B. So all the rays that leave E end up at B. And that's what imaging means. Okay, you're forming a one-to-one map. E goes to B. Okay, but the key point to appreciate is that any other point on the object will not be imaged perfectly. So I can design these two surfaces to perfectly image F to A and E to B because I have two surfaces. But if I pick any other point in between, let's say a point here, it will have an approximate point here, but in general, it will not be perfect. You will have aberrations. So it will be a little bit blurred here. And this is what's referred to as image aberrations. And you can, of course, correct for them, but you need more than two surfaces in that case. Okay? So for perfect imaging, one would need infinite surfaces. For perfect imaging for infinite points, one would need infinite surfaces or perfect control of refractive index, which is in general not possible. So, which is the reason, by the way, if you open up the camera in your phone, you will see not just a single lens, you will see a stack of 6 or 7 lenses. So these 6 or 7 lenses are designed very, very carefully in order to minimize all the aberrations, so in order to get a very, very high quality image. But even then, of course, they're not perfect. As you can probably take a picture of something, you can zoom in and see the aberrations with your own eyes. So real lenses for always forming perfect images or images with aberrations. So keep this in mind, because this is in a non-imaging setting, this will no longer be important. So now let's think about how to bridge the gap between imaging and non-imaging. Okay. So again, we come back to a very simple example. You have a source. Now the object becomes a source, like the sun, let's say. It's all the points are between E and F. Many rays here, R1, R2, R3, R4, R5, all coming from different points. And then you have, let's say, a lens, simple lens, and then you have a receiver, AB. Okay. Now, and of course, in the case of this, in this particular example, the lens has two surfaces. Okay, so this is air, this is glass or plastic, and this is air again. However, if the edge points E and F are imaged onto A and B respectively, now what does that mean? That means if I design this lens with two surfaces such that I have a perfect one-to-one map of F to A and E to B, which I can do, as I said in the last slide, right? If I only care about 2 points, I can actually design a perfect imaging system. Then we can postulate that if I pick any ray in between, pick any point in between here, okay, and draw a ray, okay, which is what's shown here, I can postulate that that ray has to end up somewhere in between A and B. Okay, we don't know exactly where it'll be, but we can say it'll be between A and B. In other words, it'll be in the region of the receiver. Okay, all the rays from the intermediate points must pass in between A and B. Then, if you think about it, I have actually collected all the energy that's coming from EF and assigned it to AB. I don't know exactly where it goes, but I know it will end up at AB. This is a non-imaging optic. Okay, the lens in this situation acts as a concentrator. Of course, in the diagram I've drawn, it's a demagnification, so I haven't concentrated it. They actually reduce the concentration, right? But you can imagine, sorry, I actually have concentrates. I've taken energy from a large source like here and set it up in a small receiver here. So I have concentrated light, but no image is formed. Okay, there is no one-to-one correspondence between the points on the object and those on the receiver. So this is a non-imaging design problem, and it's a much simpler design problem. So that's the good news. The imaging is much harder to do. Non-imaging is generally easier to do. Of course, there are situations where it becomes very complicated. Okay, so that's something you have to think about a little bit. Now let's consider the situation when the source is large and far away, which is of course the case of the sun, right? If in this situation, if I take my source EF and move it to infinity, move it towards the left here, as far away as I can, then all these rays start becoming parallel, right? Because they're really, really far away. They start looking like this. I have rays which come like this, passes through my lens, focuses to one end of the receiver, and I have rays which come from the opposite direction, opposite side, and they pass through the lens and gets focused to the other edge of the receiver. Okay, parallel rays D1, which represent the edge or one edge of the source, let's say the sun, gets focused to one edge of the receiver. The parallel rays from the other edge of the sun, so it gets focused to the other edge of the receiver. Then I can say that any ray in between, okay, I can draw parallel rays in between at different angles between 0 and theta and 0 and minus theta. I can postulate that all those rays will end up somewhere in between here as well, between A and B. But they need not be focused to the same point. In other words, I can draw parallel rays at, say, a smaller angle here. All I can claim is that they will be, all those rays will end up somewhere in between. They may not end up at the same point. Okay, if they end up at the same point, that means you have a very, very nice imaging system. But in a non-imaging problem, you don't need to have them end up at the same point. So all rays in between end up in between A and B, but need not be focused to single points. Okay. So of course, if you think about this, this is a simple concentrator, right? So if I take a lens and take sunlight and focus it, this is what I would get. In other words, if the sun is moving, say this is one rays from one edge of the sun, and this is the rays from the other edge of the sun, and they form. And a lens can form the image of the sun. So AB now becomes the image of the sun. But what's nice about non-imaging optics is you don't need to form the image of the sun. If you use a single lens, of course, you can form the image of the sun imperfectly. Okay, so now let's try to understand this, the most fundamental form of a non-imaging optic, which is referred to as a compound parabolic concentrator. It's not a lens. So in this example, I told you, in this example right here, when the sun is far away, and this is a lens, this is the image of the sun. Although it's imperfect, it's the image of the sun. Like I said before, you don't need to form the image of the sun in order to collect its energy. So the compound parabolic concentrator here is an example of a non-imaging optical element that does not form the image of the sun, or whatever it's trying to collect its energy from, but it can collect its energy. So let's take a look at what it means and how we design this. And we'll use this as an example to understand the fundamental concepts of non-imaging optics. Okay, so let's begin with a brief introduction using this video from Edmund Optics. So let me see if I can play this first. So it gives you an idea of what the non-imaging optic, the compound parabolic concentrator looks like and what it's used for. Okay. Oops.
collect and concentrate divergent light while avoiding the difficulties associated with multi-element system? If so, compound parabolic concentrators, known as CPCs, may be the choice for you. A CPC is a concentrator designed using a rotated parabolic shape. The wide end of the CPC collects divergent light, which is then reflected within the CPC and concentrated at the narrow output end. CPCs are defined using an acceptance angle, which is the angular range in which a CPC can collect light. CPCs are ideal for any application that requires the condensing of divergent light sources and are commonly used for solar energy collection, wireless communication, and biomedical and defense research.
Okay, so the CPC is a very good and simple example because it allows us to understand how to design out imaging optics. But it's also a very useful example because this is it can be theoretically shown, at least in 2 dimensions, that the CPC is the most efficient geometry one can use for concentrating light. Okay, and we'll talk about that. So it's a very important example to understand very clearly. So let's think about what are we trying to do in non-imaging optics. Our design goal is to concentrate incoming radiation to the maximum extent possible with the highest efficiency possible. Okay, what does that mean? That means if you have a radiation source, which is shown here by E1, and it has lots of rays coming out from all its points, you want to collect it on some receiver of an area AB, which is generally smaller than E1. Okay, so the receiver is generally smaller than the radiation source. The radiation source, let's say, is the sun, it's huge. The receiver, let's say, is our solar cell, it's small. Okay, you want to ensure that all the rays of light coming from the source end up at the receiver. That's the key idea. Okay, how do we do this? So let's start with a very, very simple idea first. Okay, let's imagine a ray of light here, R1. Okay, this is coming from the sun, let's say, coming down, and this is our receiver AB. Okay, it's also referred to as an exit aperture because what we are designing in is an optical element, and it's the output aperture of the optical element, and we can put our receiver right here, like our solar cell. Now, what happens if we put a mirror here? Essentially, this ray, R1, is reflected by a mirror put at an angle beta to the horizontal. Okay, this ray will reflect down as shown here, and we adjust this angle beta of this mirror such that this ray ends up at one edge of the receiver, point A. Okay, and let's assume that R1 is the largest angle that you're hoping to receive. Okay, and of course this angle theta here, which is the incident angle of R1, determines the acceptance angle of our optical system. Okay, but right now our optical system is very simple. It's just a mirror sitting like that. Right? Okay, the ray which comes here ends up at this point. So of course you can calculate what the angle beta is given the angle theta and the size of the receiver. Okay, it's a very simple geometry problem. Now, in the case of symmetry, in order to maintain symmetry, we're going to take this mirror and put it on this side also as a mirror symmetric design. Okay, so BD1 is a mirror, AC1 is its mirror symmetric design. All that means is that if I have a ray which is symmetric to R1 but coming in this direction, it will reflect at this point and end up at B. In other words, I can take this ray and flip it, and I will get the same thing. I've only drawn one here for clarity. Otherwise, there'll be too many lines. Okay, so now our optical system is very simple, right? It has two mirrors at an angle beta of each other, and that's it. Our input aperture is this, and output aperture is that. And we have actually concentrated light, right? Because we have collected light from a large input aperture, C1, D1, and put it into a smaller output aperture, AB. Okay, so that's a very, very simple concentrator. In fact, this is very similar to what we had in our solar cooker. Okay. In fact, we can also show for maximum concentration. If you think about this geometry here, in order to increase the concentration, what one could do is one can decrease beta, right? Because I want to take this ray and spread it to as large of a point here as possible. That means I want to reduce beta. I want to make this as shallower angle as possible. Okay, and of course that also means my entrance aperture C1 D1 gets larger and larger if I reduce beta. If I tilt this down, my D1 moves towards the right, C1 moves towards the left, and my C1 D1, which is my entrance aperture, gets larger and larger. Right, and if AB remains the same, that means my concentration is increasing because I'm collecting from a larger area. Okay, but of course there is a limit, right? So can someone think about what happens if I make this arbitrarily small?
Reflect.
Yes, exactly. The ray will essentially hit this mirror and reflect out of the system. Okay, we'll see what that looks like. It'll do this, right? If beta is too small, I put this down, this ray will look like this, right? It will end up hitting the mirror on the other side, and it will reflect off the system. So it will not reach the receiver. This tells me now that there is a minimum number for beta, okay, which defines the maximum concentration I can hope to achieve. So if beta is too small, the edge ray R1 will miss the receiver. Okay, in other words, the angle beta must be chosen very carefully based on the acceptance angle theta, which is this angle here of the ray, and the size of the receiver, AB. And you can work out the geometry. It's not that complicated, but you can do that. But our goal is to actually keep going. Our goal is to try to increase the concentration somehow. So to prevent this, what you can do is you can actually add one more. Is there any questions before I go on? Okay, I guess not. So we can add one more mirror. Okay, so let's say you have a mirror beta 1, BD at an angle beta 1, which is AC1 here. But now you add one more mirror, a slightly larger angle, beta 2. Okay, so I have a mirror here, BD1, and I added one more mirror, D1, D2. Okay, now what happens is that this ray here ends up here as we originally intended. And we have another ray here, which is parallel to this. So this is still an edge ray. Okay, these two rays are parallel. Because this is slightly tilted with beta 2 slightly larger, it now bends such that it also ends up at A. Okay, so this ray ends up here from this mirror. This ray ends up here because of this mirror, because its angle slightly larger, beta 2. Okay, now what have I done? And of course, there's also an equivalent on this side, C1, C2, it's mirror reflected. Now, what have I accomplished here by putting two mirrors? What I have accomplished is I have increased the entrance aperture. So if it's one mirror, I had an entrance aperture of C1, D1, okay, that size. By putting one more mirror, I've increased the entrance aperture to C2, D2. You can see it's a little bit larger. Now, if my entrance aperture is larger, while my receiver size is the same, that means I have increased my concentration, right? Concentration factor is defined as entrance aperture divided by the receiver size, and receiver size doesn't change. So if I increase the entrance aperture, I've increased the concentration. Okay. by adding one more mirror, I have maximized the new entrance aperture to C2D2. Now, you can see where this is going. I can keep adding more mirrors, right? I can add another mirror slightly tilted, another mirror slightly tilted, and so on and so forth. And I can create a surface here. Okay, that's where we're going to. And we'll see that this surface here is a parabola. Okay, well, we'll see this shortly, such that its focus of this parabola is this point A. So these rays here coming parallel, reflects off this parabola, gets focused to this point A. And this side is also a parabola, but it's reflected such that any rays which come this direction gets focused to the point B. Okay, so we'll see this shortly. So similarly, we can keep adding mirrors, and these mirrors can be infinitesimally small. This means that we can trace out a reflective surface or a curve. Okay, so what has happened here is that I've taken these mirrors, which you can see are discrete lines here, and made them really small, really tiny, so they become infinitesimal, and this becomes a smooth curve here, a smooth parabola, as shown here. Now, the few things to keep in mind, that there is a symmetry about this vertical axis. In other words, this curve here is reflected here, mirror reflected about the vertical axis. The angle beta has to be minimized at each point on this curve, which we saw before. Angle beta is defined as the angle of the ray at any point here. Sorry, the tangent of the surface with respect to the horizontal. Okay, remember, this is essentially the tangent to the surface of the curve. Now you can also show that this is the same, this is also the curve that produces the smallest beta and largest entrance aperture, in this case C3D3. Okay. Okay. So let's review what a parabola is. So I told you before that this is now a parabola, such that rays of light which come parallel here gets focused to the point A. Okay, so let's review what a parabola is. This is a parabola, which we've all seen in our high school physics. Light comes in straight down in this space, and it gets focused to a point F. Okay. Okay. Excuse me, I need to get some tissue. My nose is running, so give me a minute, okay? I'm just gonna run and grab a tissue. Hold on. Yeah, did you hear me, Subhashish?
Yeah, sure.
Okay, just give me 1 second. Sorry. While I'm out, think about the geometry. Okay, I'll be right back.
Okay. Do you have any idea? Do you have any idea? I mean, you told him to think about. Well, thank you. Okay.
Okay, I'm back. Sorry, I have a cold. So, can you hear me?
Yeah.
Okay, so to review the parabola, the definition of a parabola is that any ray, that any line that's drawn parallel to the axis of the parabola, essentially after reflecting of the parabola, will end up as its focus. So Q1, P1 goes to F, Q2, P2 goes to F, Q3, P3 goes to F. So any ray that comes parallel to the axis of the parabola. So that's the axis of the parabola, okay? And you can also see this from an optical path length point of view. If you have the path length Q1, P1, F is equal to the path length Q2, P2, F, Q3, P3, F, and so on and so forth. If you recall, when you drew a parabola in high school, you actually potentially have done it by putting a pencil here and putting a string which is attached to the paper here and to here, and you move the pencil like that. In any case, the parabola has its axis parallel to the edge rays and its focus is at A. Now, for the CPC, you think about this parabola and you have to rotate it a little bit, okay, which you can see in this picture. So this is our parabola that we just looked at, okay, this line here. So just focus on this line that I'm pointing out with the mouse, okay? And then we're going to truncate this parabola here, okay? So we're going to ignore these dashed lines, only focus on the solid line of the parabola right here. And this parabola has a focus here, A, okay? What that means, and of course, the axis of this parabola is now this line, right? It's parallel to this line. So if I have a ray of light which comes in like that, it will hit this parabola and end up at A, or FA. So I have a ray which is parallel to this line. It will hit this parabola, end up at FA. Another ray parallel to this line, it will hit the parabola, end up at FA. So if I have a string of rays coming down in this direction, they will all hit this parabola and end up at this point A. Okay. Now I also have a symmetric parabola on the other side, which is shown by this curve. Again, I'm pointing it out with my mouse, okay, which is truncated here, shown by the solid lines, and the same thing happens. So this is the axis. The rays come down this way, reflects off this parabola, and ends up at its focus, which is now FB. So all the rays which come this way end up focused at this point. Okay, so now you can see if I have these two parabolae, I can have any rays that come into the system, they will always end up at this point or this point. Okay, as long as they're coming at an angle that is parallel to this axis or this axis. Now, what happens to the rays in between? So I have rays that have a slightly smaller angle. You can actually show from the edge ray principle that we saw before that they will always end up between these 2 points. So this is equivalent to saying that these 2 points are now perfect images of the edge rays coming from the 2 edges, whereas anything in between will form imperfect images in between those 2 edge points. Okay, so now, of course, it's a non-imaging optic. We don't care about forming an image. So as long as they're in between, we have collected that light. So that's a good thing. So we have achieved our design goal. Now we have to define a few parameters here. So first of all, this D1 is the entrance aperture of the CPC. Okay. This axis, vertical line here, is the axis of the CPC. This D2, which is the exit aperture of the CPC, or the size of the receiver or the solar cell. Okay, and this theta here is the acceptance angle. This is theta is generally defined as half the acceptance angle. Okay, this total angle is the acceptance angle of the parabola, which means that any ray which comes at an angle within this cone defined here will be collected by the receiver. Anything outside this cone will not be collected. Okay, and this is a little bit of an abstract or geometric idea, so you need to kind of look at it and think about it a little bit. So I would highly recommend you to kind of look at it, think about it. It's quite important for you to appreciate and be able to understand conceptually how this works. Okay. Excuse me. Okay, now let's keep thinking about how this CPC can be improved, okay? What happens if I keep extending the parabola? So I can remember, as I said before, I was adding, we were adding mirrors to it, right? What if I keep adding the mirrors, keep going up and changing the beta, as I was saying before? Turns out that they, of course, start curving inward, right? So you can see they start bending inside. And the entrance aperture now starts decreasing. Okay, so C4D4 is now less than CD, which means shadowing starts to occur. Okay, so that's not good, right? You're going to lose light, which basically means that this height of this CPC, there is an optimum value, right? Or a maximum value that you can hope to achieve. Okay, and that of course also determines the concentration factor, as we will see next. Okay, so now let's try to summarize the key idea here, okay? And this is the very most fundamental idea in non-imaging optics. It's referred to as an edge ray principle. What does it mean? So let's state it first and then try to appreciate what it means. Light rays coming from the edges of the source must be deflected onto the edges of the receiver, okay? If we are able to do this, then all the rays in between will end up at the receiver. This is the basic design principle of non-imaging concentrators. So let's think about what this means again. The rays coming from the edges of a source must be deflected on, it can be reflected, refracted, there are many ways to do this, but let's just call it deflected for now, onto the edges of the receiver. Okay, this is what a CPC does, right? It takes this ray, which is an edge ray, right? This ray right here, and it deflects to the edge of the receiver. Okay, this is the largest angle one can hope to collect. So that's an edge ray, and this is the edge of the receiver. It reflects off here and ends up here. Same thing on this side. This is the edge ray, reflects off here and ends up at the other edge of the receiver. Okay. So that's an example of an edge ray principle, such that your edge rays end up at the edges of the receiver. So any other ray in between will end up in between the edges of the receiver. So you will have ended up collecting it. And that's what's referred to as the edge ray principle. So again, to say it very simply, if you in order to design a good non-imaging optical system, what you need to do is you need to look at the largest angle rays that you want to collect. Okay, these are referred to as the edge rays, and you want to ensure that the extreme or the edge rays end up at the two extreme edges of the receiver. And if you are able to design a system to do that, then anything in between will automatically end up at the receiver. That's the basic idea. So it's a fairly simple concept. Okay, so let's see how this works. So this is a CPC. So you have an example of an edge ray here. Okay, this is parallel to the axis of this parabola. So it reflects off this surface and ends up at the focus, which is this point. Okay, and this is the axis of the parabola, of course. That's theta. Okay, that's an edge ray at theta. What if theta 1, we come in at a smaller angle? So this is a ray which is shallower than the edge ray, or theta 1 is less than theta. So you can see it reflects off this receiver and ends up here, somewhere here, in between the two edges of the receiver. So you have actually collected it, so that's good. What happens if theta 2 is greater than theta, which means it's outside the acceptance angle of the CPC? Come this way, reflects off the surface, reflects off the surface, reflects off the surface, and escapes the system. And that's the basic idea. So what this is saying is that if I design the edge ray to focus at the edge of the receiver, I can collect anything with an angle which is less than the edge ray angle. If it's greater than the edge ray angle, it leaves the system. So to summarize that again, all rays entering the CPC with an input angle less than theta are trapped and end up at the receiver, but all rays entering the CPC with input angle greater than theta are lost or reflected back. So you can define this mathematically with a very simple function called the acceptance function, which is defined as the number of rays reaching the receiver, which is can be thought of as number of rays accepted divided by the number of rays entering the CPC. And this is 100% or 1 when the input angle is within the acceptance angle cone, minus theta to theta, and it's 0 if it's larger than the acceptance angle. Theta is called the half acceptance angle because it's half of the angle. So theta is defined as here. This is half of this cone. Of course, it's symmetric, so it's, you have on the other side as well, so it's half of this cone. Okay, so in a CPC, this is true. In fact, mathematically, you can show this is true, which means that the CPC is an ideal concentrator because you get 100% efficiency and nothing outside the acceptance angle. Okay, so CPC is an ideal concentrator. We can also think about this problem from an imaging point of view. Okay, and what I mean is the following. You can look at it from the optical path length point of view, as we said before. We know for a general parabola, as shown here, you can take any ray which comes parallel to the axis, so that's the axis of the parabola, AC, it will end up going through the focus F. Okay, and BD will go through the focus F. We can show in a parabola the optical path length AC plus CF is equal to BD plus DF. Okay, that's true for any parabola. Okay, C plus CF is BD plus DF. This is the equivalency coming from geometry, nothing to do with optics, right? This is just pure geometry. Now, you apply this geometrical principle onto the CPC. Okay, so that's our CPC. You have light ray here, ED. Of course, it reflects off this parabola and ends up at A. Okay, and you have a light ray here, CB. It reflects off the parabola and also ends up at A, right? This ray is parallel to this ray, so they both have to end up at A. Angle is theta. So now we can apply this principle here. ED plus DA, okay, this is ED plus DA, should be equal to CB plus BA, which is basically the same thing here. Okay, again, let me say ED plus DA should be equal to CB plus BA, just from pure geometry. Now we know that CD is A1, let's call it A1, which is the entrance aperture of the CPC. And AB is A2, the exit aperture of the CPC, okay? So then we can write CB, so CB plus A2 is equal to ED plus A1. Okay. Sorry, ED plus DA, not A1, sorry. But CB, which is this line here, CB is equal to AD, right? Just from the symmetry, you can see CB is equal to AD or DA. And A2 is equal to ED. A2 is equal to, oh no, this is not right. A2 should be equal to AB, so this is a mistake, so ignore that. A2 is equal to A1 times sine theta. Let's see how that comes. So A2 is here, is A1 times sine theta. So So theta is this angle, which is the input angle. Okay. A1 is this. Sine theta is ED divided by A1. So ED is A1 times sine theta. Oh yes, and ED is the same as A2. You can actually show that because this is an isosceles triangle, so you can actually show that yourself. Okay, so A1 over A2, which is the ratio of the entrance aperture to the exit aperture, which is also the same as the concentration factor, is now equal to 1 over sine of the theta. Okay, this is a very, very important conclusion here. A1 over A2 represents the concentration factor of the GPC. It's the input aperture divided by the output aperture is equal to 1 over sine of theta, theta being the acceptance angle, half acceptance angle of the CPC. So what this is saying is that if I want large concentration, which means I want A1 over A2 to be very large, I need theta to be very, very small, right? They're inversely related, which means, what does that mean? That means if I want very, very high concentration, I need to track the sun very precisely because I can only let in a very small angle of light. If theta goes towards 0, I can get this concentration factor to be almost infinity. That's the idea. Okay? And you will see this trade-off again and again as we talk about concentrators. Now, the whole derivation here is based on this idea of the optical path length between the wavefront CE and the focus A is the same for all edge rays perpendicular to CE, right? So, in other words, the CE represents the wavefront of light coming in. So, if you draw any ray which is perpendicular to the wavefront, it needs to end up at A, the focus. So, you add up the optical path lengths of any of these lines, they should all be equal. It's based on that principle. Okay, so I want to make sure this derivation is clear to everyone, but it's pretty simple, right? From this equation, CB plus A2 is ED plus DA, just from the geometry. But CB is equal to DA because of the symmetry, so you can cancel out CB and DA. Then we know A2 equals ED. If A2 equals ED, ED is also A1 times sine theta. This is A1. And then A1 over A2 becomes 1 over sine theta. So relatively straightforward. Okay. Any questions about that?
No.
Okay. So again, I know I went through many of these things pretty fast, so I would recommend that you go and do it yourself so you can get a better appreciation. So let me also point out, it's important that you do it, most importantly because these are fundamental concepts that you should understand, but I will probably ask you something about this in the exam as well. So just make sure you're clear about it. Okay, there's one other parameter of the CPC that we still need to design, which is the height of the CPC. In other words, how tall is it? And that's also related to the concentration factor. So let's try to figure that out. The H, which is the total height, can be divided as H1 plus H2. Okay, H equals H1 plus H2. And then you can simply relate this. H1 is A1 divided by 2. So if you look at this triangle here, it's A1 divided by 2 divided by tan theta. So tan theta here is given by A1 divided by 2 divided by H1. And H2 is given by A2 divided by 2 divided by tan theta. Okay. So you get this very simple expression. You add them up, you get H equals A1 times 1 plus sine theta over 2 tan theta. So in other words, if you knew what the entrance aperture was and you knew what the acceptance angle was, you can very easily calculate what the height of the CPC is. Now you can see a very important relationship here. As theta increases, in other words, if I increase my acceptance angle, my height of the CPC also has to get larger. And this is not a good thing in general, because if you want your CPC to be very tall, this becomes very bulky and difficult to install if you want to use it as a solar concentrator. Okay. On the other end, if theta goes to 0, in other words, you only accept a very narrow range of angles, then H becomes almost infinity. So, okay, so there is a mistake here also. So let me just clarify this. As theta increases, H actually decreases, not increases. So this should be flipped. So I made a typo here, which is obvious. As you can see, the tan theta, as theta increases, tan theta will increase and h has to decrease. On the opposite end, as theta goes to 0, h goes to infinity, which you can see from this expression. As theta goes to 0, tan theta goes to infinity, right? So very, very small acceptance angles means very large concentration. CPC becomes very, very tall. So let me summarize what this means. If you want very high concentration, you have to give two big penalties. One, your acceptance angle becomes very small, which means that you can only get a small fraction of light coming straight through, and you have to track the sun very precisely if you're doing it for sunlight. Number two is that your CPC starts getting very tall, and it becomes more impractical for installation. Okay, two very important conclusions. Now, the CPC, as I said before, is an ideal concentrator in 2 dimensions, but you can also imagine using it in 3 dimensions. There are, of course, 2 different ways to use it, many different ways to use it. 2 examples are shown here. One is that you can simply take a parabola and rotate it about a central axis, and this is referred to as a paraboloid, 3-dimensional surface. Or you can use it this way, where you have an X parabola, a pair of X parabola and a pair of Y parabola, and you essentially have an intersection between them. Okay, so you have a parabola in this side and this side, and you intersect them. Okay, but in all cases, it can be shown that the CPC is a very good concentrator in 3D, but it's not perfect. In other words, you will always have some skew rays within the acceptance angle that are lost. Skew essentially means that rays that are at an angle to both planes of interest. So if you take an X, a plane, the 2 planes orthogonal to this surface here, you have a ray coming at some strange angle. That's referred to as a skew ray. Okay, so in other words, the acceptance function of a CPC in 3 dimensions is never perfect. It's not 100%. Okay, so I want to stop here and talk about and continue the rest of the non-imaging optics on Thursday, but I want to make sure I give you some guidelines for the presentation 1, which is due next Thursday, so you have enough time to prepare for it. Okay, so so let me just quickly point out. First of all, the online team will create a video or screen capture with audio of the presentation, submit a video file. It's due on September 28th. All of the teams in class will present on September 28th. And the goal is you will have a 10-minute presentation with 5 minutes for Q&A. And these are the main steps I need you to cover. Number 1 is a literature review, where you discuss the pros, cons between existing technologies or solutions, identify the main problems with the current technologies. And this is basically what you did in your assignment 1. You're probably going to flesh it out into a few slides and be able to explain it very, very clearly, okay, with some references. The steps 2, 3, and 4 are related to your assignment 2, which is due September 22nd. And and again, you need to flesh those out into slides. Number 2 is list the results of your brainstorming session, which means that you need to have a brainstorming session. Present at least maybe 3 or 1 to 3 crazy or novel ideas. Try to be creative, but of course be careful of the physics. Number 3, pick your top idea. It can be more than one, but I would generally pick your best idea to focus on and describe it in some detail. Explain why this is novel and what problem will this solve. So when I say describe it in some detail, you don't need to do any crazy analysis, but you want to go into some more detail than what you did in your brainstorming session. So you need to spend some time on that. I would say 1 or 2 slides on that. And number 4 is then think ahead a little bit. If this is the idea that you're going to implement, what challenges do you expect to encounter when implementing this innovation? And think from a both technical and non-technical manner. Of course, technical will be easy for you, I think, but and it's important. But non-technical is also important. It's a little bit harder, so you should start thinking about it. And think about how will you overcome these challenges, and provide a rough plan. Like how would you bring your idea into the world? Okay, and all of these are a part of assignment 2 as well. Okay, I think we'll stop here and let me see if there are any questions. We have about 10 minutes or so. If there are no questions, then I will let you meet with your team and plan ahead for your assignments. If there are any questions, let me know. And I want to go through this material a little slowly because it's a little bit abstract, even though it's simple, and I need you to think about it. That's why I don't want to rush through it a little bit. Okay, I guess then we'll stop here.
Thank you.
Thank you.
Thank you.